All right, thank you. Everybody can hear me okay, and you can see the screen all right there? The slides showing up? All right. Yep, sounds good. All right. Well, thank you, Chris, and thanks a lot for pulling this together again as well and continuing to support the code change updates and training partnership. Very much appreciate that, and appreciate everyone making the long commute in, as Chris did this morning, to our laptops for another day of adventures ahead. So yeah, as Chris said, we're going to cover the mechanical system requirements and then start to go into a little bit more detail about modern equipment options and some of the implications of equipment choice in regard to code, and then also just what we're seeing out in the market right now and trends of where we're heading equipment-wise. So this is basically going to be a summary of Chapter 3, general requirements of the code, as well as the mechanical system requirements that are in Chapter 4, which is kind of the meat of the code. Again, understanding that the code is designed as a design document, a lot of this is looking at how to properly plan and lay out and design for mechanical systems within residential buildings. So Chapter 3 in the code, sections R302 through 305, covers the design conditions for residential construction. So we're looking at what the building load design conditions are, parameters for entering data into load calculations, material system and equipment requirements, including installation requirements for different mechanical items in the building, the design criteria for ventilation, and also touches upon combustion safety requirements for any fuel burning equipment within buildings. So, Chapter 4, the mechanical system requirements covered in Chapter 4 get into more of the details about controls and piping and ducts, more of the details on ventilation, testing requirements, for coming up with the basis for design. So interior design conditions are called out in the beginning of Chapter 3. So these are the basis of what you're actually using as a set point for internal temperatures in the building for heating and for cooling. So that's called out in section R302.1. And also, you need to be knowing what the design conditions are for external temperatures for your winter and summer design temperatures, design conditions. So that's the table shown in R302.2. So our winter design temperature is -11, and summer design for cooling is 84 degrees. If you want to get into the details, there's climate data that is available through local regional airports as well as other data points if you start looking online. So if you want to dial in the temperature data for design temperature for a specific locality, that's certainly the best route to take. I mean, there's certainly a difference between design temperature in Brattleboro and design temperature in Jay. So these are things that certainly affect the comfort and overall energy use for equipment in buildings. So here's a big important item that stands out buried in the code. This comes from Chapter 4. So this is in the middle of the Chapter 4 energy efficiency section of the code, R304.8. And this is the basis of design for sizing equipment. So this is industry standard. This follows other national codes that AKA Manual J be used to, or other approved heating and cooling calculation methodologies used to create the basis of load design for new systems or new buildings, as well as using other AKA manuals that cohabitate with Manual J, such as Manual S and Manual D, for sizing of the actual equipment and distribution design. So what is Manual J? Well, Manual J is a basis for design, essentially. You know, this is what it needs to be done and should be getting done for any building and any system replacement in a building. so that we can get accurately sized and accurately functioning equipment into buildings. So AKA is the Air Conditioning Contractors of America. Manual J is actually the load calculation process for building design loads or block loads. So this is basically what the maximum heat loss or cooling demand on a building would be on the hottest or coldest day of the year. And that's why we're using those local design temperatures noted in the previous slide. So this gives what the worst case conditions would be for the building, what the total maximum amount of heat loss would be occurring and heat input would need to happen in a building, as well as cooling in the worst case conditions for the climate of the building being built in. Also, Manual J will give you, and the right tools that use Manual J as a basis will give you room by room load calculations. So, it's important to both have the block load of the building to understand the size of the equipment you want to be looking into putting into the building. But then room by room load calculations are also crucial to be able to understand what your distribution equipment design needs to be. We need to understand how many BTUs of heating or cooling need to be gotten into each room in the building. So that's where the other AKA manuals come into play here, where AKA Manual D is actually for distribution design or duct design. It's distribution design, but as a basis here, and as you can kind of tell from the name, this is the Manual D is kind of focused on ducted heating systems and cooling systems. The basis design for room by room load calculations is important and crucial for hydronic system design also. And also AKA Manual S is a manual we're using for actually sizing and selecting appropriate equipment for the loads that you come up with for the building. So Manual J, accurate load calculations are crucial for any new building especially, and also should be getting done for any, like I said, system replacement. That's also a requirement called out under code. So that's been in the code for many, many years. And there's certainly implications for not paying attention to accurate load calculations, especially now as we are certainly seeing much lower design loads with buildings because of the requirements of code and just general industry adopted standards for construction at this point. We have new buildings that have much lower loads than they used to be, much less air leakage, much better performing building envelopes. So that has significant implications on comfort when you're not paying attention to sizing methodologies. So oversized equipment, what are the reasons for this? You're making a guess on the load, not doing proper load calculations if you are doing the load calculations. As we start to look at modern equipment options when it comes to heat pump equipment especially, sizing equipment based on extreme conditions can throw things out of whack during the bulk of the heating season, and we're going to kind of get into some of those details further on here. And then just using the rules of thumb that seems to be an approach that has gotten traction in the HVAC world of, people have experience obviously, and that is crucial to getting well-performing systems. But experience on what's worked before doesn't necessarily mean that it's going to work again or it's going to work for a specific building. So actually doing the calculations is crucial to get the right outcomes. So some other trickle-down impacts of oversized equipment: uneven temperature control and discomfort. You don't want unhappy humans in the building that they've spent a lot of money on to invest in. So making sure that they're getting accurate or appropriate temperatures across the different rooms in the building is pretty elemental. It's the basis of putting a heating or cooling system into a building. So, what this can come out to be in the real world is you can have cycling of equipment that creates noticeable temperature swings in the building, especially for forced air systems. Short cycling has implications on the equipment as well as comfort. Oversized equipment can have impacts on humidity control in a building if you're not moving air properly and you're expecting that HVAC system to run for ventilation purposes also, which we'll cover some of that further on. as well, the combination of ventilation and heating and cooling into the same duct system. And, you know, high cost, you know, we can keep systems for buildings pretty darn simple at this point, and using old methodologies without careful calculation can lead to installation of equipment and systems that may not necessarily need to be there or be as complex as they need to be. So what are we looking at for inputs here? This is just kind of shows what some of the impacts are from high to low of accuracy within a load calculation. Design temperature is crucial, getting the right design temperature input. The building envelope, windows, doors, ceilings, those accurate calculations have a major impact on what the accuracy of your load calculation that you end up with, your design load you end up with. Infiltration and ventilation have, you know, impacts in the middle ground. And then as you see in the bottom, some of these other things certainly come into play, but have lower impacts than the items above. This is a screenshot of some of the items that you're going to be looking at in a design load calculation, in a manual J calculation. So these are inputs that are going to be put into the spreadsheet to come up with your load. There's a lot of tools available out there in the market to either do a full-on manual J load calculation, or again, as it calls out in the code, another approved methodology. And these are not major investments. You know, you can get free tools that may not give you an actual manual AKA approved document in the end, but RightSoft, which is kind of the industry standard for doing HVAC design and load calculation, you know, $300 gets you an annual subscription to use that. There's other tools that are $100 to $300, so it's not a major investment, especially if you're an HVAC contractor, to get the tool to give you these design documents at the end. And as it's called out in the code specifically, these are the maximum oversizing limits allowed under RBES. So for AC and heat pumps, maximum oversizing of 15%, and for fuel-fired equipment, maximum oversizing of 40%. You know, oftentimes you do see a lot of buildings that, you know, the default is putting in a modulating condensing boiler that has a modulation range from, say, 20,000 BTUs to 120,000 BTUs. But if that building's maximum design load is really only, say, 50,000 BTUs, you have a system that can still meet the load at 50,000 BTUs, but is massively oversized from the majority of the heating season, which has significant impacts on equipment performance and overall energy use. So just because it's modulating doesn't mean that it's modulating in a way that you want to get the best performance out of it. And when you have equipment that's oversized and the return temperature is coming back into the heating appliance higher than it needs to be, then the system's not going to be condensing at that point. So this is kind of an example of showing the impacts of that. So these charts are showing essentially what the heating load would be on a building annually, and the number of hours on the bottom of temperature within a certain range, and then the actual heat load on the vertical axis here. So if we're looking at the left square here, this shows, you know, the total heating load on the building for the annual for the total year. On the right, what we see is that about 80% of the heating season, you're not even coming close to the maximum design load temperature for the building. So the bulk of the heating season, you're going to be needing to use less of the maximum potential of your heating appliance to satisfy the demand for the building. And if you're designing for maximum load, you need to make sure that the equipment that you're sizing to meet that maximum load is going to also work efficiently then when you're not hitting that peak, because the total number of hours that are actually at design temperature or near it are pretty darn small when you look at the numbers, and that goes for heating and for cooling. But, you know, given that we're a heating demanding climate here, that's kind of what we focus on. You know, if you have a design temperature of -11, maybe there's 100 hours annually where you're actually at that design temperature. Probably going to be a lot less. And as we start to look at heat pump equipment as the direction that a lot of buildings are heading in, we have to be careful about sizing and specifying equipment with that factor in mind. So an implication of this is an example from a building that's gotten to be pretty famous. This was a multifamily building in Chittenden County where it was managed units. So the building owner was the owner of the units and paid for the utilities. And there were it was subsidized tenants, so they had to be careful in managing what the operational costs were going to be for these units. So these are 3 different load calculations that were done for the building. Or actually, there's 2 load calculations, and then what was the actual final installed specification. So these were the BTU per hour per square foot loads that were calculated initially by an engineer that were for each of these rooms. So 3-room units, these were the loads that they came up with based on assumptions and not on actual understood design conditions for the units, but based on assumptions. Then that calculation was redone a little bit tighter based on what the actual design conditions were for the units. And you can see these numbers were basically cut in half. But then the old methodology of padding those numbers for, covering your butt on the cold days and not wanting the callback were added to this. And this was all individual heat pump units. So each room was getting its own heat pump, which makes it even more significant of an implication. So this is what was actually installed. So equipment that would do 38,000 BTU per hour per square foot, common area 23 in these other rooms. What ended up happening here is that the equipment was constantly short cycling because the load was never as high as the equipment that was installed. So instead of having efficient heat pump equipment running, basically these units were being heated by electric resistance heat because the heat pump was coming on and off, on and off, on and off, and it never ran in a modulating fashion. So this is just an example from the field of how those implications, what those implications can be for taking assumptions rather than careful load design. So any questions on that section? Good. So that's just the basis of thinking and requirements around design for loads for the building. Another section to note from section 305, R305, is that any home that's being built compliant with the 2020 RBES, adjust that, sorry, is considered as of unusually tight construction as designed by the national fuel standards. So basically this means that any fuel burning combustion appliances that are in a building need to be direct vented or have combustion air provided to that appliance. We can't just use atmospherically vented chimneys anymore, but that's pretty much a no-brainer because that's the equipment option that we have available to us now. Electric resistance heat. So this is something that's specifically called out in the code now as far as application. Essentially, buildings heated with electric resistance heat are prohibited. So that means meeting the whole building load with electric resistance heat is not allowed. So electric boilers, electric resistance baseboard, you can't heat a whole building that way. Any heat pump equipment used in residential buildings needs to be certified as cold climate equipment. And if there is any supplementary electric resistance heat, that equipment will only run as a defrost in the equipment. So what is allowed, and this is sorry, the slides are advancing without my input here. Electric resistance is allowed in certain circumstances. So electric resistance that's being replaced in existing buildings, that's still an allowable use. But where it actually comes into play for new construction here is limited areas where other heating sources are cost prohibitive or impractical. So if we're talking about conditions which are defined here, where buildings that are you're using a cold climate heat pump as the primary heating system for the building. And we'll talk about some of those design options with heat pump equipment or other non-fully distributed heating options. You can still use electric resistance heat in spaces that are not reached directly by the distribution of the central heat pump equipment. So that can mean, bedrooms that are not ducted from a heat pump or don't have a heat pump head in it, or other distribution, bathrooms, things like that. But there are these conditions that are specifically called out. So that means that the electric resistance will not turn on if the whole building load is being met by the heat pump. So that's what this kind of references here, that as long as the outdoor air temperature is 5 degrees or higher, the heat pump equipment will be meeting the whole load for the house. So the electric resistance needs to be inoperable at those temperatures or higher. And it also requires that the building be a tighter envelope than what base code would require. Base code requires 3 ACH 50. If you're going to be using this electric resistance option, the building needs to be 2 ACH 50 or better. And there is a specific call out for multifamily buildings, where if you have multifamily units that have low design loads per unit, less than or equal to 6 BTUs per hour per square foot, at design temperature at -11, then those units can be heated with electric resistance heat. Any questions on that? All right, so we're going to jump into mechanical ventilation requirements for buildings. So we're talking about actually moving air within the building for the occupants, not ventilating building assemblies for moisture management here. We're talking about a whole house ventilation. So whole house ventilation systems are required, are mandatory for any new construction. So these systems can be exhaust only, or they can be balanced, and we'll discuss what is triggering a balanced system versus exhaust only. But base code requirements just call out exhaust only as the base requirement. So there's two ways of approaching this. You can either follow the code requirements in section 304 prescriptively, which I'll show you the table next. Or you can actually do calculations for the building and size the equipment based on what the actual house and occupants would require, which I'm going to be biased and recommend you go that route. So this is the prescriptive fan requirements for the building. So you can meet the code prescriptively with base code if you have a 3-bedroom house and you install a single bath fan that's rated for 100 CFM in the building. So 3 bedrooms, 1 bath fan, 100 CFM, that will meet the base requirements for the code. If it's a 2,800 square foot house, 3,000 square foot house, and you have 1 bathroom with a fan located in the master bathroom, and you're using that as your whole house ventilation system, you might not get good air quality management throughout the whole building, but you can still meet the code that way. So alternatively to meeting the building ventilation requirements prescriptively, there's the performance option. So that means actually doing calculations to come up with a ventilation rate and flow requirement for each building based on number of occupants, its size, its location, etc. So these are the 3 accepted calculation standards that can be used: ASHRAE 62.2, the Building Science Corp standard, and the Passive House ventilation requirements. So ASHRAE 62.2 is the most common method used for determining ventilation requirements. This is a tool that's available here from Residential Energy Dynamics. This is online. You can just follow this link and it'll take you to this tool right here, these inputs. So it's pretty straightforward. You're putting in square footage, occupants, height of the building. If you have a CFM number for air leakage estimated, you can put that in there. That dials in the number even better. So this will give you what your total fan capacity is, what size fan rated equipment you should be putting in, and the number of hours per day that you should be setting that thing up to run to get the proper ventilation rate for the building. So this is all very simple equations, very simple inputs. You have that data from the design documents for the building. You should be able to get this for any building easily. It's the same as the manual J, approach. You can't just go off the idea of, well, this unit from Brown says it can ventilate a 3,000 square foot house. That's the one we're going to put in. You should be getting to a little bit better detail than that. So beyond the whole house building ventilation requirements, there are local ventilation requirements called out in section R304.8. So this basically means that building or rooms in the house, bathrooms that have tubs, showers, spas in them need a ventilation option in there to remove excess humidity during the times those bathrooms are in use. And so this is the local ventilation requirements called out in table 304.2. If you're going to have a standalone fan in that space as the local exhaust, that fan needs to be moving 50 CFM if it's going to be on or off based on occupancy or load. And if the bathroom local ventilation requirement is going to be met by a ducted, fully distributed ventilation system within the building, it needs to be moving 20 CFM minimum if it's going to be continuous. So it's good and important to be able to actually test flows within buildings and understand that they're actually, moving air as you intend them to be, because the fan itself is designed to do a job, but it's only one part of the whole system. So, when you look at what your system's options are, again, you can meet the building code requirements for base code with an exhaust-only system, or you could install a balanced ventilation system. Exhaust-only systems suck. That's just their job. They suck air out of the building, and if you have a tight building envelope, there's less air to make up for it for your quote-unquote fresh air, and you're getting that fresh air through wherever the building can be, air can be drawn from. But again, that's allowable under the code, but there are certain applications in the code that do mandate balanced ventilation systems. So if you are in a jurisdiction like South Burlington, where stretch code is the local code requirement, you have to be doing balanced ventilation. If you're going to go the res check path rather than prescriptive, you're going to need to do balanced ventilation. If you do the UA alternative to the prescriptive R value requirements, you're going to have to do balanced ventilation. And there's certain points options with the points requirements for prescriptive that are moving in the direction of balanced ventilation. So if you can sense a theme here, we're moving in the direction of balanced ventilation, and there's a good reason for that. So we're going to touch on what those reasons may be. But if you are going to be putting in balanced ventilation into a building for any of these reasons here, or you need to understand that there is performance requirements for that equipment. So an HRV or ERV has to have an electrically commutated motor in it, an ECM motor fan. So it's basically a modulating speed fan rather than a fixed speed fan. So you have to be looking for a specific model that's going to have that performance. The manufacturers have plenty of options. The rub right now is availability locally. They just haven't been stocked to this point for the most part at suppliers, but we're working with suppliers right now to get more ECM models available in stock rather than having to order them in. But manufacturers certainly are keeping up to demand here on that front. And there's minimum performance requirements for efficiency. So 70% SRE for HRVs and 65% for energy recovery systems. Any questions on that? Coffee. Just need my coffee break. Okay, controls. I'm not going to go through this in detail, but R304.8 calls out the specific control requirements for ventilation systems. So essentially, the gist of this is it needs to run automatically without a human fiddling with it. We see a lot of ventilation systems installed in buildings that don't get used because the occupants have turned them off or they've turned off on their own because they've never had the filter changed or cleaned. For inaccessibility, or because the owner doesn't even know that that needs to be done. Or another implication is, like I said, you have a ventilation unit, a fan or a balanced ventilation unit, a box that is designed to push a certain amount of air and recover a certain amount of heat, but it's only one part of the system. And poor duct design for the ventilation system can lead to noise. It can lead to discomfort. So those are other reasons why occupants will turn off a ventilation system. So careful layout of ducts to actually get a well-designed system is crucial. But R304.8 covers those control requirements in the code. So what are we trying to control with mechanical ventilation? What's the purpose of this? So it's occupant indoor air quality, trying to manage things, pollutants within the building, as well as moisture. You know, moisture is a big thing now that we have tighter building envelopes, and it's especially impactful within the first few years of the house being built, because it takes a long time for buildings to dry out. There's a lot of embodied moisture in buildings, especially concrete and foundations. So managing that humidity in the building is highly important. There's definitely times where condensation is good, but then there's also times where condensation is bad, and then there's times where condensation is really bad. So managing moisture in buildings through ventilation is kind of the biggest thing I try to message to any builder, because these are trickle-down impacts that you're not necessarily going to be aware of or thinking about as you're putting the building together. But this is, you know, there's plenty of things that can go haywire and wrong if you're not paying attention to the function of the whole building as a system. You know, these images here are not strictly just the result of not good ventilation in the building, but it is a consequence of not managing indoor relative humidity well, along with some inadequacies in the building envelope too. So building as a system, right, Chris? So integration, you can do a ducted ventilation system that has its own duct system moving through the whole house, independent of any other system, or you can combine, if you have a forced hot air cooling AC system in the house, you can design the system so the equipment shares the same duct system. So there's some pros and cons for each. But you have to be aware of what the equipment can do independent of the duct system. So HVAC systems for heating and cooling move air in a way different than what HRV and ERV systems are designed to do. They're two different boxes with two different flow rates and two different intentions. So when you combine those two pieces of equipment to do the single purpose, you have to be careful in your consideration of how they're going to end up functioning in the end. And specifically in the code, if you are going to be integrating ventilation equipment, HRV, ERV, into a ducted heating system, in section R403.6.1, what this requires is that, as it's called out earlier, as I mentioned, the HRV or ERV has to have an ECM motor. But if you're using the ductwork of the heating or cooling system, then you're going to be relying on the blower motor of the heating and cooling system to move ventilation air most of the time. So code specifically calls out then that that blower motor in your heating HVAC system needs to be an ECM motor also to be compliant with code. So there are these trickle-down implications, but certainly something to be aware of. So this just kind of covers some more of those details of the combination of equipment, some implications to be considering when you're looking at a design that combines the two. Ultimately, in the end, you know, really what you should be able to be looking at is be able to balance the system as it's installed. So there should be dampers and other things that can regulate flow within the duct system, and then be able to measure those flows. You know, measuring flows and knowing that you have a balanced system is crucial. And you know, you should have a exhaust and a supply that's within about 10% of each other when you're actually measuring the flow rates of equipment within a building. It's pressure balance, and pressure balance is crucial in any duct system, whether it's ventilation or heating and cooling. You need to have an equivalent amount of air returning back into the system as you're supplying to the building. So the next few slides here just show some of the standard design options, and I'm not going to go through these in detail, but we're going to provide the slides here, and there's some other documents I've provided to VBRA previously that kind of go into more detail to reinforce this. But your standard standalone system, you have a supply side and you have an exhaust side. Again, you're looking at these numbers here of CFM delivered. And again, those totals, if you're actually doing a duct design, these total numbers should be equivalent to each other or very close to. So that's the bottom line when it comes to flow rates. So the most common method for combining two is putting the fresh air into the return side of the furnace ductwork, and then the return air to the HRV has its own ducts. There's the supply side, so there's the other option of putting the fresh air into the supply for the forced air system for the building. There's return supply. There's return. So can't expect everyone to know all of these options in detail, but it's a conversation that you should be having with your mechanical contractor if this is the system that they're proposing. If they're proposing to do a combined ducted system, just be thinking and referencing back to some of these caveats I've mentioned. Is the equipment designed in a way that it's going to work within one of these combined methodologies? And the equipment manufacturers have those methodologies called out in their installation documents also. And also, the balancing of the equipment, the testing of the flows, and options for adjusting flow rates within the duct system. Any questions on that? Nope. Okay. And a couple more items specifically called out in section R304. Clothes dryers. If it's a standard clothes dryer, it needs to be ducted outside. Can't be just blowing into the building or ducted into a garage. It needs to be ducted directly outside unless you're using a heat pump dryer or condensing dryer. Another one that's been in the code since 2015, R304.11, makeup air. If you have a range hood in a kitchen that moves 400 CFM or greater, you need to have a makeup air system installed so that when that range hood is turned on, an equivalent amount of air that range hood is going to be sucking out of the building is actually being brought in to keep the building within balance. So that's been in the code for a while now. There's equipment options available on the market to integrate the functions of those two things. But ideally, if you can get a range hood in that's moving less than 400 CFM, that's going to alleviate a lot of headaches for you. 200 CFM is plenty of airflow in a range hood to do its intended purpose of removing pollutants and managing humidity and smells and everything else. Another section in the code that specifically calls out some performance requirements that can be overlooked are requirements relating to fireplaces or wood-burning equipment within buildings. So fireplaces that are going to be site-built or wood stoves or other internal combustion equipment like that being put into the building need to have gasketed, tight-fitting doors covering the firebox. There needs to be combustion air directly to the firebox, whether it's a site-built masonry fireplace or a wood stove. So these are some important details that need to be accounted for. If you are putting in a fireplace, you can't just have an open hearth like we used to before. There's a lot of reasons why, it's important to pay attention to these requirements and make sure that these are followed. Again, you don't want angry clients that are having Thanksgiving dinner and they fill the whole house with soot and smoke. So heating and cooling duct system requirements. There are call-outs for performance for ducted systems. So our sections R304, basically that covers the prescriptive and mandatory requirements for performance of the installation of ducted systems. So installation of ductwork, sealing of the actual equipment itself, of air handlers, duct testing. So duct testing is required for duct work that is outside of the thermal envelope of the building. So you have two options for testing. You can test the equipment at rough end before the building's complete, or you can test the building at the very end when everything's all done. There are different leakage requirements or maximums for leakage through the duct system based on those two options of testing. So a way to avoid having to do any duct testing for a HVAC system is to just ensure that all of the ducts and the duct system itself is fully within the building thermal envelope. So keeping the ductwork within the building thermal envelope and following the actual duct sealing procedures, it doesn't mean that you can forego sealing of the actual joints and connections of the ducts or the air handler itself. That's all mandatory. But if you can keep that ductwork within the thermal envelope, you don't have to worry about the testing. You cannot use building cavities as ducts or plenums. So stapling up tin to the bottom of a floor joist is not an acceptable return for the HVAC system. In order for ducts to be considered within the conditioned space, you need to meet these two requirements here. You need to be completely within the continuous air barrier and within the thermal envelope. And any ducts that are within that thermal envelope itself, they need to be buried with insulation in accordance with R403.8 which covers what those insulation requirements are. It's the next slide. And an important call out here is the ceiling insulation R value installed against and above the insulation or the ductwork needs to be greater than or equal to the R value less the R value insulation of the duct. Basically, try to get, if it's an R49 attic flat, try to get the insulation around the ductwork to R40. So that is more specifically called out here in section R403.36, ducts buried within the ceiling insulation. So the duct itself actually has to have insulation wrapped around it of R8 minimum, and then buried within the ceiling insulation to R40. So best practice principles for duct design, as I said, any equipment, whether it's if it moves air, if it's ventilation equipment or if it's heating and cooling equipment, the unit itself is designed to move a certain amount of air at a certain flow rate at a certain static pressure, but that's just what it's designed to be able to do. The duct system is the system side of it that actually allows that equipment to do its intended purpose. So duct design is just very frequently and often overlooked, and the implications of that are pretty significant. So, making sure, as again, we're talking about this as a design document, if you can look at the plan set with the HVAC contractor and have a conversation as to where they're going to put their ductwork in the drawings, then they don't have any surprises when they show up to the site to do their rough in and there's a paralam beam running down the middle of where they want to run their trunk line, or there's a header that they can't go through to run supplies to one section of the house where they thought they could before. So let's go for predictability here, try to get, the system design and the duct layout understood before anybody starts digging a hole. But, these are some basic, just fundamental principles of good duct work and good duct design. And one thing that comes into play here is oftentimes you need more space than you might think to get appropriate flows throughout a house. Trying to center the air handler within the building eases design and eases layout and performance. So try to get this stuff ironed out before you start bringing subs to site, because no one likes spiders in their attic. And just because the flex duct becomes in a 25 or 50 foot length doesn't mean you need to use all of it. So, let's try to avoid these sorts of situations if and when possible. I just had to throw some of this in here. I mean, this is how much airflow are you think you're getting through this sort of snake? And fans vented into a main trunk line coming in at T's. The turbulence of the air in these junctions here just it degrades the performance of the equipment. You can have, at the other end of this pipe right here, you could have the best HRV or bath fan running available, but because of this, it's not going to do anything that it was designed to do. So options, you know, the principles that we're talking about here cover any sort of equipment option that you're going to use for creating heat or providing cooling. I'm going to talk about some of the heat pump equipment options here for ducted systems, because, you know, we are moving in this direction of strategic electrification, switching from a fossil fuel-based heating, you know, economy towards efficient electric. That's policy that's coming into play, but it's also a practical implication of the building performance that we're getting now. We're getting buildings that, again, have much smaller heating loads and cooling loads, and fossil fuel equipment puts out more heat often than the building needs. So again, you can have a modulating boiler or furnace, but, you know, that modulating boiler or furnace is meant to work at its best efficiency when it's at the higher end of its spectrum of output. So if you're putting in equipment that's never going to really use its high end of BTU output, you're never going to get the true rated performance of what you're buying or what you're putting into the building. So when we look at some of our options for heating buildings with heat pumps, doing centrally, you know, distributed systems. So this is, you know, we're looking at options that are going away from putting mini split heads throughout the building. We're talking about, you know, fully distributed or centrally distributed systems. So centrally ducted heat pumps. So this is essentially basically, you know, an HVAC air handler, but it has a refrigerant coil from an outdoor condenser unit. So these are designed Mitsubishi. There's an option shown here for a 3-ton unit for a standard centrally ducted system. So it does have higher static pressure capability, means that it's kind of designed around standard duct layout and design. Has an ECM motor, so it's modulating in that regard for its output. So these are options for looking at whole building ducted systems. And there's more equipment coming to the market now. So this is different than, you know, a split heat pump outdoor condenser unit that's being put into a fully distributed ducted system that has a fossil fuel furnace feeding it as well. You know, that's certainly an option as well, but you're more reliant on the fossil fuel equipment. This is an option for eliminating that fossil fuel equipment and just using the heat pump as your main heat source for heating and cooling the building. Then there's the option of compact ducted or ducted mini splits. So this is essentially using the same type of outdoor condenser unit that you would for a mini split, but using a ducted distribution rather than mini split heads. So these are designed around lower static pressures, so smaller ducts and minimal duct lengths, but it's good for creating zones within a building. So you can, you know, rather than having a heat pump in 3 different bedrooms in each room, you can centrally locate an air handler here and duct into those rooms. So it's a slightly lower performance than straight up mini splits. You can't beat the efficiency, raw efficiency of a single head mini split, but single head mini splits aren't always the best option for small load rooms. And that's, again, going back to the design philosophy here, why it's important to know the room by room load calculations. So what are we talking about here in actual look and function? Again, using Mitsubishi as a reference point. An outdoor condenser unit, and then this is your indoor air handler. So it's small compact units that are designed around fitting into floor systems. So you know, you can put them up into ceilings within a closet or a hallway space, and then duct from that point. Again, the static pressure is lower here than it would be in a standard duct system. So again, this is kind of referencing what I was speaking about before, where, you know, you buy a piece of equipment that's designed to create a certain amount of heat or cooling at a certain amount of flow. And so the actual design of the system to provide that happens in the field. And so it does take careful design, and you know, you've seen a lot of ductless mini splits installed because it doesn't take that level of design to put in a mini split, but you don't get the right performance necessarily with a mini split for low load rooms, as we mentioned. So this is kind of just reinforcing some of what I spoke about a few minutes ago. Again, AKA Manual D is the actual design methodology for duct design, distribution design. So that's always a good place to start. And a good quote here to reinforce these items as a rule of thumb: it's not a good idea to use rules of thumb for HVAC design. And as I've tried to sprinkle in here too, you know, with the ASHRAE tool, the Manual J tools, there's other tools out there that are accessible and open source and free to use that help you dial in some of these system designs. So static pressure calculators, that's available here at BRI-AIR. Follow that link, it will bring you to this tool where you can start to input some of the duct inputs to get your design for diameter, length, number of bends, etc. So utilize tools wherever possible. One of the things to just briefly show here on the performance side of things. So again, knowing your room by room load calculation or room load is crucial for good design. And that goes for whether it's going to be a forced air system or if it's going to be a hydronic system. Knowing what each room needs and knowing that you're adequately supplying that room is crucial. So multi-zone heat pumps were pretty popular, or have been, where you have one outdoor condenser unit that's feeding, say in this situation here, the potential 3 indoor mini split heads. It seems like a good clean option where you just have a single condenser. You don't have 3 different condensers outside for 3 different heads. But there are impacts on output of heating and what that means to the individual rooms that are being fed by that single outdoor condenser. So turn down ratio is the big thing here. So we're looking at different design temperatures we're talking about. So outdoor conditions and what the load would be and what the output would be for the equipment. So let's say we have a bedroom that needs 12,000 BTUs of heating at 5 degrees outdoor temperature. In this situation, on the right here, we're looking at a compact ducted unit. And on the left, this is the multi-zone single condenser outdoor unit. So we're looking at a mini split head in the bedroom with this situation. And we're looking at a duct coming from that central air handler in this situation. The mini ducted system will put out at a maximum 12,000 BTUs at 5 degrees. The split system here will put out at a minimum 12,500 BTUs at 5 degrees. So equivalencies here at 5 degrees, the mini split option with the single outdoor condenser would meet the bedroom load at 12,000 BTUs with the mini split, and the ducted system would meet it at its maximum capacity at 12,000 BTUs. But then we get up to 47 degrees outside. Now at 47 degrees, that bedroom is going to need a lot less than 12,000 BTUs. It's probably going to need, you know, half of that. At 47 degrees outside, that single condenser multi-zone heat pump unit is still going to be putting out close to 12,000 BTUs. That compact ducted unit is going to be putting out, you know, 3/4 of that, 8,100 BTUs. So what this means is that in this situation, the turn down ratio for the compact ducted unit is going to be a much better match for what that room load's going to be versus what the single condenser multi-zone mini split head unit would do. So in this situation with that single condenser unit, you'd be putting out far too many BTUs than the room needs. The outdoor unit is probably going to be short cycling, coming on and off because it's putting out too much heat than the building needs at that time. Whereas the compact ducted unit is going to be a much better, closer fit, and it's going to still be working in its modulating range and being a better match for load for the room. So these are design conditions that need to be understood, especially with heat pump equipment, you know, what you're designing for as far as total load capacity, and making sure that loads are going to be met evenly at different temperature ranges. So this is just the, you know, again, reinforcing the idea here that a multi-zone single condenser unit with 3 mini split heads trying to condition 3 different bedrooms versus the philosophy of using a central air handler in the hallway that's feeding the individual rooms off of one head. Better load control with this system than with this system. Are there any questions? Nope. Okay. So bottom line, compact ducted can be a better option than a multi-split. Using these things to be considerate of and making sure that you have access to the unit itself, make sure that you have access to the air filter to be cleaned and maintained, and access to the air handler for maintenance. So last section here we're going to get into is hydronic distribution options. And quite a bit of detail here on the hydronic options because I'm kind of biased in that regard. I'll be honest about that. I think there's a lot of good reasons to look at hydronic system options for the future. And also to just reinforce the idea that, you know, we have many different ways of heating and cooling buildings now efficiently, and equipment options to do so. So what we're getting at with any hydronic system now is aiming for low temperature distribution. Standard fin tube baseboard is about 180 degree water that you're moving through the building in different ways. You can have series loops, you can have parallel loops, but ultimately your output and the whole system basis is around creating hot water that's being distributed throughout the building. Where we're at and where we're moving is in the direction of lowering that delivered water temperature as much as possible. There are many options for delivering low temperature water throughout a building, and the lower you get the temperature that you're actually delivering to the building that will meet the loads of the individual rooms and the total load for the building and keep the occupants happy, the more options you have for heat sources, for equipment in the end. And again, this leads to future-proofing, as I see it, and many others do, is that it's a way of designing a distribution system that's going to be viable independent of what equipment you plug into it, what's available now or what's available in the future. So any load temp design for hydronic distribution can be met with air source heat pumps, ground source heat pumps, condensing boilers, biomass systems, district heating. You know, even if you're still in the direction of using combustion fuels, combustion equipment, low temperature design is going to give you the actual condensing boiler that you're paying for. You know, it's going to, when you make sure that you're getting low return temperature back into the boiler, then that boiler is actually going to be condensing as it's designed to do, and you're actually going to get the rated efficiency out of the equipment instead of it not ever doing that because you have imbalance of temperatures. So one of the things I'm going to get to here in the next couple slides is just showing you the comparison of delivered heating capacity in water and fluid versus air. It's pretty significant, and what that impact has on overall distribution energy within a building. And as I said, properly designed and installed hydronic distribution systems can last for many decades, and they can outlast many different iterations of the heat source that you're using. So water is vastly superior to air for conveying heat. And this just reinforces a couple different ways of looking at it. So these calculations here are showing the heat capacity of a volume of equivalent volume of water versus air. Shows you that an equivalent volume of water and air, that water will hold 3,500 times more heat than the same volume of air. Functionally within a building, here you go. This kind of shows you the implication of how it lays out. You need much more surface area and size for forced air distribution than you could even come close to needing for the equivalent amount of heat delivered in water. So it has a lot of trickle-down implications in the design, layout of the building, and performance. So just a brief look here of going through distribution efficiency and again kind of reinforcing this thinking of what you get for what you pay for air versus water. And if anybody wants to dig into this further, John Sigenthaler is kind of the man when it comes to low temperature hydronic design. He's an engineer from New York State. He's worked with NYSERDA as their programs closely for many years. He's written the design manuals for space pack air to water equipment. He's a great resource, and I recommend anyone who has interest in this to dig into the content that he's developed over the years. So efficiency is, output over input of energy necessary to deliver that output within the building. So you're taking the rate of heat delivery divided by the rate of energy use required by the distribution equipment. So as an example he uses here, so we're talking about a large heat load of 120,000 BTUs per hour design load, using 4 circulators to move the water throughout the building to meet the load demand, and they're operating at 80 watts each. So a total of 320 watts at design load at the worst case conditions for meeting that 120,000 BTU design load for the building. So that comes out to, you're getting 375 BTUs per watt of energy consumed to deliver that heat through the building. So what do we compare that to? So looking here, the comparison he uses is taking a 4-ton rated geothermal water to air unit. So this is forced air distribution, where you're taking the the heat from the ground, the geothermal system, and creating a hydrocoil that you're blowing air across to do forced air delivery throughout the building. So in this example, you're getting 48,000 BTUs of heat delivered with a 1 horsepower ECM rated motor that's consuming 746 watts of energy to move that 40,000 BTUs of heat throughout the building. So that gives you 64 BTUs per watt of energy consumption, compared to 375 BTUs of watt energy for the hydronic distribution. So you're getting a significantly higher amount of energy or delivered to the building for what the actual distribution system's consuming to make that happen. And from an actual hydronic design, you can see here that this is with a home run design where you're actually feeding each individual room and each individual heating appliance within the building with a straight supply and return from a manifold, which is best practice for hydronic distribution design. At this point, you're getting 11 zones of heating here, consuming 27 watts of energy, delivering 1,600 BTUs per hour per that watt consumed. So, that's all that single circulator is using to deliver that amount of heat throughout the building. So overall end energy use is significantly less than what you can see with forced air systems. Now, that being said, a lot of people go forced air because the client wants AC. Modern heat pump and low temperature hydronic systems can be utilized with air to water equipment to do heating and cooling within the same distribution, within the same supply system. An air to water heat pump with a buffer tank, you can use that buffer tank as a hot water battery essentially for the heating season. And then that tank can be used to create cold water during the cooling season. And with appropriate equipment put into the building for distribution, you can get cooling demand also. So there is flexibility in this equipment and these distribution options to meet both of those demands. But you really can't argue with the efficiency of the low temperature hydronic design. So what are we saying when we mean low temperature distribution? This is a pretty good visual here that kind of shows the distribution options for different equipment that'll work within a temperature range. Low temp distribution, we're really talking about a maximum of 120 degrees water delivered to the building. At the far end of the spectrum, fin tube baseboard, this is the temperature range we're talking about, 160 to 200 degrees delivered temperature. At 120 degree delivered temperature or below, you can see you have a lot of different distribution options. You have radiant slabs of different types. You have tube and plate, which are different radiant systems you can do in walls or ceilings or other ways. Panel radiators, low temperature emitters. So there are plenty of good distribution options for lower temperature water. I left this slide in here just to show, again, reinforce what the, design philosophy for heating would be, of looking at your, output at different temperatures. You should be looking at your equipment outputs at different temperatures, and then deciding which distribution option you want to use within the building for low temperature. So there's quite a few different ways of looking at this. You have your standard radiant floor heating system, offers consistent low temperature heat. You really only need about 90-degree water going through a standard, well-insulated radiant slab to get occupant comfort and good occupant comfort in a well-designed, code-built or better building. So consistent low temperature heat. There is lag time in recovery if there's going to be changes in the room settings, but the beauty of radiant heat too is that if you get the right set point and everything dialed in, everybody should be comfortable without needing to make significant changes, because the room's not going to cool off or heat up quickly because of the design of the building envelope. So low temperature, high output baseboard is another distribution option. Looks like standard fin tube baseboard, but it works with lower temperatures. There's a lot of equipment available on the market, readily available, that provides this option. Panel radiators, common worldwide. A lot of Europe and Asia uses this type of equipment, so it's not like it's a new technology being put out onto the market. But basically, essentially, what it is you're getting much more surface area to allow that lower temperature water to be exposing its heat to the room and to the occupants. One of the other cool things you get with some of these panel radiators and other distribution equipment options is you get room-by-room control. You actually have thermostatic control on the radiator itself. So that's how you can, each occupant can have their own comfort level. It's like your, what do they call it, the beds, that you can have your own dialed-in sleep number. So you can have your dialed-in comfort number and temperature also. Fan coil units, so it's kind of like a mini split where you have, a hot water hydronic coil moving through the unit, and then a blower motor and a fan that's moving air across that hot coil to move heat into the room. So this can be used as an alternative to panel radiators or low temp baseboard. This can also be used in a cooling application also. And then panel radiators with fan assist, it's similar to the previous option. So again, you've got the surface area of the hydronic coil within the unit itself, and then a fan blowing air across that to more distribute air further into the room. And then I didn't cover here, the other radiant options, which can be wall panels, it can be ceiling panels. So there are many creative ways to provide distribution with low temperature water within the building. So, hydronic systems and designs don't need to be complex to work well. And in fact, the less complex, the better. So, this isn't what we should, we've become accustomed in some ways, I think, to seeing complexity within hydronic designs, and complexity is a hallmark of performance, that you're getting this high-end system, installed in a building. But, all of those different circulators and pumps use a lot of energy beyond what you're just burning for fuel to create the heat. So moving in the direction of simplicity not only makes sense for long-term durability and maintenance and performance, it's also the best fit for the loads for the building. So here's an air-to-water system. This was a retrofit actually installed by a colleague of mine over the past year in his own home. He went from a gas boiler that was feeding a radiant slab and then fin tube baseboard in the bedrooms on the second floor, to replacing the fin tube with low temperature emitters, some panel radiators in the bedrooms, utilizing the radiant slab, and putting in a Nordic air-to-water heat pump. So this is what the mechanical room looks like now. You've got the actual heat pump unit itself. You have the buffer tank, the storage tank for the heating load, the battery essentially of hot water, and you have a heat pump water heater. And here's your manifold for distribution. So pretty simple, pretty clean, not complex. Simple is better. And as an example for performance from Brian's project here to show you what the actual performance was of some of this equipment. So this plot data here shows the coefficient of performance or the efficiency of the heat pump at different temperature ranges. So a coefficient of performance of 1 is essentially electric resistance heat. It's 100% efficiency. For 1 watt of electricity consumed or 1 kilowatt of electricity consumed, you're getting 1 BTU of heat. So anything greater than that, you're getting more heat for less energy consumed. So most of the heat pump, air-to-water heat pump equipment available on the market right now is rated at about a 2 COP at 0 degree outdoor temperature in that range. So this is actual monitored performance data from Brian's system. And you can see at 0 degrees, the coefficient of performance was definitely above 1, close to 2. So even at those low outdoor temperatures, and you can see this is the majority of the heating season right here is in this range, 20 to 30 degrees. That's where the bulk of the heating load for the season is, as I showed on the slide at the very beginning here. And the COP in this range is between 2 and 3. So you're getting 200 to 300% efficiency out of the heating system for this house for the bulk of the heating season. In the overall system design for air-to-water equipment, as you get below 0 degrees and you get below temperatures that are, the performance of the heat pump starts to be impacted, you have in the buffer tank here a 20,000 BTU electric resistance element that is in there to help maintain temperature in the tank when the outdoor heat pump unit is still able to meet temperature in here, but it may not be doing it as efficiently. So, there's basically what you're getting is insurance to make sure that you have enough hot water at a sufficient temperature for the distribution within the house, no matter what the outdoor temperature is, no matter what the heat pump can do. But when you're looking at the total number of hours that you're going to be below its ideal performance range, it's pretty negligible. But you have the backup into the system design baked in. And this just shows you similarly what the output of the heating equipment was at the different temperatures. So, at 0 degrees outside air temperature, you're still getting between 20 and 30,000 BTUs of heat. And I think Brian's design load at minus 11 was 35,000 BTUs. So, he's getting, and that's at design temperature. So again, most of the heating season, his design load is probably, in the 20,000 BTU range. And you can see that the heat pump is more than making up or more than providing what the building would need for heating energy during the bulk of the season. So any questions on that, on low temp hydronics? And again, design. Okay. We're coming up on the last couple slides here. And again, so the low temperature hydronic design, it applies to any heating input. It doesn't have to be air to water heat pump. It doesn't have to be a geothermal system. You can just get best performance out of a condensing gas boiler with low temperature design. So just the last couple items to make note of from the code directly. Pipe insulation is required on supply side for heating equipment within the building and protecting the pipe insulation. There are requirements around domestic hot water performance and circulation systems. I won't go into these in detail since we're coming up on time. So read deeper into this or read through this as you get into the slides that we'll provide to you at the end. But just be aware that there are some requirements around domestic hot water, recirculation, pipe insulation, same. So basically, if you have hot water pipes in the building, there are insulation requirements for those pipes. So who's got your back? This is just a gratuitous opportunity to put Bill Murray into a slide deck. And but getting at the point that if you got questions, want to talk about this in more detail, discuss specific designs, please reach out to us, to myself or my colleagues here at Efficiency Vermont. We'll work with you on some, design considerations, options, put you in touch with hopefully the right people who can actually design and install a system for you, and plenty of background data to back up options. So thank you. Appreciate the time.